In this video, we're going to explore the idea of resonance structures further. In the last video, we evaluated 3 different resonance structures of SCN- using formal charges. So here, we're going to look at resonance structures in more detail. Resonance structures are equivalent Lewis structures which are the exact same except for the placement of electrons. And so we might have more than one Lewis structure for the same compound, and some of these structures contain differing double or triple bonds, or the bonds existing in different places. And we're going to look at how resonance structures can affect some of the properties of these compounds. And so we're going to take a look at first at the molecule of ozone, which is O3. When we're writing the Lewis structure for ozone, it turns out that we could have a single bond between the first 2 oxygens and a double bond between the second 2, or our double bond could be between the first 2 with a single bond between oxygens 2 and 3. We will look at the idea of bond lengths in more detail in a later video, but for now, know that double bonds are shorter, stronger bonds than single bonds are. And so, when we're looking at O3, with a single bond between 2 of the oxygens and a double bond between the other 2, we would expect that the oxygen-oxygen double bond will be a shorter bond than the oxygen-oxygen single bond. And so you would think that this resonance structure here would exhibit one long bond and one short bond. Likewise, you might expect that this resonance structure would have one short bond and one long bond, but between 2 different oxygens. It turns out, though, that experimental observations have shown us that those 2 bond lengths are actually the exact same. Not only that, but those bond lengths are between the length of a typical single bond and a typical double bond. And so we have these 2 resonance structures showing where the electrons could exist, but experimental evidence shows us that what really exists is perhaps some hybrid between the 2. So let's take a look at what that means. Here we're going to look at another example. So we're going to take a look at the Lewis structure for the carbonate polyatomic ion. So we could write out one Lewis structure that would look like this. And would have formal charges of -1 on each single bonded oxygen. We could also have a resonance structure that instead places our double bond between this carbon and oxygen, which once again would give us formal charges of -1 on each of our singly bonded oxygens. And we would have a third option that exists, placing our double bond between the carbon and this oxygen, which once again gives us formal charges of -1 on each of our singly bonded oxygens. We represent resonance structures by placing a double arrow like this between the structures. Now again, when we look at experimental evidence and experimental data for the carbonate polyatomic ion, what we actually find is that these 3 bonds, these 3 carbon-oxygen bonds, are not different in length as these structures would imply, but they are in fact equal in length to each other, and that length is somewhere between a double, and a single bond. This leads us to drawing what we call the resonance hybrid between the three. In the resonance hybrid, we draw all the bonds as single bonds, and we represent the double bond as a dashed line existing between all three. And so what this really means is that the two electrons that make up this double bond actually exist in between all and will sort of float throughout this whole entire system. And so each bond has the characteristics between a single bond and a double bond. And so this is our resonance hybrid of the carbonate polyatomic ion. We also no longer talk about the formal charges being localized on any two particular atoms, but instead we just represent that the overall hybrid has a charge of 2-. Here we're going to look at our resonance structures of the thiocyanate ion SCN-1 as we did in the last video. And so again, we would start our Lewis structure by placing carbon in the middle, single bonds connecting the sulfur and the nitrogen to the carbon. We're then going to place our remaining electrons as lone pairs around the outer atoms. But we see here that carbon does not have an octet, and so we can start by maybe placing these electrons into the middle between sulfur and carbon, giving us this Lewis structure. We also talked about that we can put the electrons instead to form a triple bond between carbon and nitrogen, or that we can form double bonds. And so these are all three valid resonance structures of the thiocyanate ion. We then went through a formal charge analysis in the last video to determine which of these is the most stable resonance structure. Those formal charges then looked like this, which led us to say that the bottom resonance structure is the more stable of the three. And so we would say then that the bottom is the biggest contributor to the resonance hybrid. And so the experimental evidence would lead us to believe that we most likely have pretty close to double bond characteristics between the carbon and sulfur and carbon and nitrogen. Another aspect to Lewis structures that we have to consider is that there will be instances in which we actually do not have an octet around some of the atoms. We might have cases where we have molecules with an odd number of electrons, which we would call free radicals. Free radicals are very reactive. In some instances, molecules may have less than an octet, such as in BF3. And in other instances, molecules will have some atoms with more than an octet. This is only possible, though, when the valence shell is going to be n equals 3 or larger. Another way to think of it is that it's only going to be phosphorus atoms or bigger that can have what we call an expanded octet. Because in these instances, the d orbitals can actually come into play to help us accommodate these extra electrons. And so let's look at some examples. So here we have an example of a molecule with an odd number of electrons. Nitrogen comes with its 5 valence electrons, oxygen comes with 6, and so we have 11 electrons to deal with total in nitrogen monoxide. And so we begin by just drawing a single bond between the two. We then start to place our electrons. We've used 2, 4, 6, 8, 3 more. In order to get as close as we can to an octet around nitrogen, we'll move 2 of these electrons into a bond, forming a double bond between the two. So we do have an octet around oxygen. However, nitrogen is only going to have 7 electrons around it, and there's no way to avoid this. And so we get what we call a free radical, which is a very, very reactive species. In some instances, we can have molecules also with less than an octet, because that's simply all the atom can fit around it. Boron is a very good example of this. And so when writing the Lewis structure of BF3, boron comes with its 3 valence electrons. Fluorine comes with its 7. And so we have a total of 24 electrons to place around BF3. So we're going to start with our boron in the middle, 3 fluorines around it, and then we're going to place our remaining electrons as lone pairs around our outer atoms first. And in doing so, we've now used all 24 electrons. Our outer atoms have an octet, but fluorine is an atom that will only ever have single bonds. You won't ever double bond to fluorine. And so in this case, our boron atom will not have an octet. It will only have the 6 electrons around it. Boron is one of the only atoms in which this will be the case. And so the moral of this story is if you have 6 atoms around boron, it's okay. Other atoms are large enough that they can actually fit more than an octet around them. And so phosphorus and larger, if that is the central atom, you can have more than an octet. And so let's look at our Lewis structure for PCl5. Phosphorus is going to have its 5 valence electrons. Chlorine is going to have its 7 valence electrons, for a total then of 40 valence electrons. And so we start with phosphorus in the middle. Then we're going to place our 5 chlorine atoms around phosphorus. And then we're going to start placing our remaining electrons as octets around our outer atoms. And we can see that we have now used all 40 electrons. Each chlorine has 2, 4, 6, 8 electrons around it. 5 chlorines for 40 electrons. Our outer atoms, our chlorines, all have an octet. But phosphorus has 2, 4, 6, 8, 10. Phosphorus has what we call an expanded octet, and it is large enough to be able to do that. Our Lewis structure for sulfur hexafluoride. Sulfur is going to come with its 6 valence electrons. Fluorine is going to come with its 7 valence electrons, for a total of 48 electrons around sulfur hexafluoride. And so we're going to start with sulfur as our central atom, and we're then going to place 6 fluorine atoms around sulfur. And then, once again, we're going to place our remaining electrons as lone pairs around our outer atoms. And in doing so, we'll see that we have used all 48 of our electrons. All of our outer atoms, our fluorines, all have their octet. And sulfur now has 2, 4, 6, 8, 10, 12 electrons around it. So sulfur has an expanded octet. And so remember, you can only ever have expanded octets in atoms that are the size of phosphorus or larger. So anything that is phosphorus or after that on the periodic table is capable of having an expanded octet. No other atom is. And so here we just see several other examples of atoms with expanded octets. Here we see silicon with 5 pairs around it and 6 pairs around it. Phosphorus, 5 pairs around it, 6 pairs around it, and so on. In this case, the sulfur atom has 1, 2, 3, 4 bonds around it for 8, but also has a lone pair. Likewise does this chlorine and this xenon atom. This xenon atom actually has 2 lone pairs around it and 4 bonds. And so these central atoms are all larger than phosphorus, or phosphorus itself, and so they are capable of having an expanded octet. And so in this video, we've taken a look at resonance structures, which are a result of having our electrons in different places in Lewis structures. And we've also seen exceptions to our octet rule. This pretty much wraps up our discussion of various characteristics of Lewis structures. Knowing how to draw Lewis structures is going to be very important for our next topic when we begin to look at the shapes of various molecules. So be sure that you know how to draw Lewis structures before we go on to start really discussing shapes, as you will have to know the Lewis structure of a particular compound in order to determine its shape. I hope this has been helpful. Be sure to come see me and get some extra practice if you still need more help with Lewis structures.